Good morning and welcome to our lesson today on kinetic molecular theory and effusion, which is going to include also diffusion, speeds of molecules. There's going to be an effusion demo, and we're going to wrap this up with Graham's law of effusion. Effusion and diffusion are two similar properties of gases, two similar processes in gases in which gas molecules are moving. And in diffusion, gas molecules are moving through each other, so two molecules are mixing. You may have run into this in biology when molecules diffuse through, say, cell membranes, moving through something else. And effusion is a slightly different kind of concept in which we have one gas which is essentially traveling through a small opening, a pinhole, and to be perfect, it has to go into a vacuum, although it doesn't always have to be perfect in order for it to work. An example of diffusion is something like food cooking, where the aroma of the food cooking can move through the house. And so if you've ever smelled dinner or chocolate chip cookies or something like that coming from the kitchen when you're upstairs in your bedroom, this would be some example of this. For effusion, the closest example that I can come up with for you is a helium latex balloon that leaks. And you know what it looks like overnight. A helium balloon tends to shrivel up and be floating halfway down towards the floor, even after the first night, whereas a latex balloon filled with air doesn't float. It will stay inflated a little bit longer. And this has to do with the fact that helium is extremely small, and we'll get to that in a few minutes. The rates of diffusion and effusion both depend on how fast those molecules are moving on average. And the average speed of the molecules is dependent on what we call their kinetic energy, or the energy of motion. And we'll talk more about that in a few minutes as well, and see how the kinetic energy will affect the molecules moving. But you can see in the diagram that the smaller purple molecules on the left in the diffusion are moving faster through that diffusion, through the red molecules, than the red molecules are moving through the purple molecules. And so it gives you an idea that the heavier molecules do move a little bit slower than the lighter molecules, and we'll talk about that in a few minutes as well. Likewise, we find that the speeds of the molecules depend on two factors. They depend on the temperature, and they depend on the molar mass of the molecules, which can be thought of as the mass of each particle. And so we'll find that the temperature, as the temperature changes, these speeds are going to change. And what we'll do in order to keep that from happening eventually, when we get to talking about some of the calculations, is we will keep the temperature constant, and we'll find that that keeps the kinetic energy constant, average kinetic energy constant as well. So here's a kind of complicated diagram that I want to explain to you. It's a diagram that shows for nitrogen molecules at three different temperatures the distribution of speeds that the molecules in that sample have. So in the blue curve, we're showing nitrogen at 100 Kelvin, and you can see that the molecules are essentially pushed towards the left, where there's a huge peak of the molecules at slower speeds, and some higher speed molecules up to a little bit above 500 or 600 meters per second. And as we go to higher temperatures, at 300 Kelvin, a little above room temperature, we see that the peak has come down, but we now have more molecules at higher speed. And for the yellow temperature, the yellow at 700 Kelvin, so about twice room temperature, we see a lot more molecules with speeds out towards 1500, 1750, or even 2000 meters per second. Now, you don't need to know the exact speeds that are going on. All I want you to notice is that these three samples contain the same number of molecules, but the distribution skews towards the higher speeds as we increase the temperature. Now, temperature measures the average kinetic energy, and so what we're going to look at is the average of these three samples. Yes, it's a little bit to the right. Again, that's not going to be important to you. What's going to be important is that you realize, to the right of the peak, what's important is that you realize that as we increase the temperature, we're going to increase the average velocity of each of the samples because we're actually increasing the average kinetic energy. So kinetic energy is given by the equation 1/2 mv squared, and for our purposes we're going to be looking at the kinetic energy and the average kinetic energy, and so it's going to be dependent on the average velocity squared as well. The average kinetic energy is directly proportional to the temperature. In fact, temperature measures the average kinetic energy in a sample. We'll talk more about that in a couple of days. And so as the temperature goes up, the average kinetic energy of the particles goes up, and the kinetic energy and the average velocity also go up. This, I talked about food aromas wafting through the house, and this is a great example of why that is. Hot aromas, the molecules in hot aromas, say coming out of the oven, do move a lot faster, and so they'll move through the house a lot faster than something that, say, comes right out of the refrigerator and is still cold. And so you'll smell the hot cookies baking in the oven before, say, iced tea that is coming right out of the refrigerator. So this speed distribution gives us an idea of how to think about molecules as the temperatures increase for the same molecule, the same mass. And we could draw curves like this for other molecules as well. You notice in the kinetic energy expression there was also a mass. So what happens if we keep the mass up? This should say constant temperature, not constant mass, my bad. What happens as we keep the temperature constant and we change the mass of the gas? And the only way you can change the mass of the gas, of course, is by changing its composition. And so we've got these three curves to show you that. They look similar to the curves on the previous slide, but they're a little bit different. The blue curve now represents chlorine molecules, diatomic chlorine molecules, a mass of about 71 grams per mole. And this looks like a slow speed gas with a lot of particles down towards slower speeds, and not too many particles even up above 700 meters per second. This red curve is that same nitrogen curve that we saw before, and so this is at 300 Kelvin, the nitrogen curve, with some number of particles up above 1,000 meters per second. And then the yellow curve now is helium, and you can see how much more spread out the helium is, with a lot more particles at speeds well above 2,000 meters per second. So as the mass decreases, we'll find that there are more particles that have higher speed, and so the average velocity is going to increase as we decrease the mass of the particles. Now think about why this should be. The kinetic energy, the average kinetic energy, is 1/2 the mass times the velocity, the average velocity squared. Keeping the temperature constant keeps the kinetic energies constant, so the kinetic energies are equal. And if you rearrange the equation, you can see that the average velocity is proportional to 1 over the square root of the mass of the particle. So as the mass goes down, as with the helium, the velocity, the average velocity, goes up. I'm calling this an inverse relationship, although it's not exactly inverse because we have that square root in there, but it's close enough for us to understand that essentially faster gas molecules, lighter gas molecules move faster, and this is partly responsible for the faster speed of helium that raises the pitch of your voice when you inhale the helium from a balloon. And I'm going to post a video for you to watch that has a description of exactly what's going on in making your voice sound a little funny. And no, it doesn't change the speed of your vocal cords, as the video will explain, and as some people think it might be. Okay, so we've seen the change in temperature, increasing temperature, increasing the speed of the molecules. We've seen a decreasing mass, increasing the speed of the molecules. And what good is all of this scientifically? Well, it turns out that we can study diffusion or effusion scientifically and use different rates to determine the molar masses of different gases, or vice versa, we can use the different molar masses to study the rates of effusion and diffusion. This demo, we have a reaction where we have ammonia gas and hydrogen chloride gas. Yes, we're calling it hydrogen chloride, not hydrochloric acid, because it is going to be a gas. Although what we do is we soak cotton wool on two ends of a long tube, and we put them into the tube and we allow the gases to diffuse. And what we're going to do is have you make a prediction. They're going to form this white solid ammonium chloride. The ammonium chloride is going to form where the two gases meet. And I want you to predict whether the white solid that forms will be more towards the left, towards the right. I guess I should also say, is it towards the middle? But obviously that's not a choice here. I'm going to have you pause the video now. And before you go on and find out the reasoning why, I want you to watch the YouTube video about the diffusion of ammonia and HCl. All right, so I'm assuming you're back from the video. If not, stop the video and go watch it now. But if you are back from it, let's talk a little bit about why what happened did happen. First of all, you should have found that the white solid did form closer to the right side, closer to the HCl than towards the ammonia. So this was the result, the white cloud of the ammonium chloride. And you notice the two red arrows are showing the distances that the HCl and the ammonia had to travel. Now, if you remember your basic physics, that in the same amount of time, something that's traveling faster will move farther. So this means that the ammonia must have traveled faster. And it traveled faster because it is a lot lighter. Its molar mass is 17.0 grams per mole versus the 16.5 grams per mole. And so the heavier gas, the HCl, moved slower. It took longer to move this, or it took the same amount of time and moved a shorter distance. And so since the ammonia is lighter, it traveled faster and farther in the same time. And when the two gases met, they were closer to the heavier gas than to the lighter gas. There will be a homework question about this using similar gases, so make sure you understand this concept, discuss it with your neighbors, discuss it with your lab partner, but make sure we do understand this concept. Okay, let's now transition from diffusion to effusion and Graham's law of effusion. So we saw the temperature was the same in the ammonia and HCl. That's important that we keep the same temperature. Everything else has to be constant except for the masses of the gases. The kinetic energies for each gas are the same because the temperature is the same. This is another important concept, that at the same temperature, all gases have the same average kinetic energies. And so what we're going to do is derive the relationship between the molar masses of the gases and the speeds of the molecules and the rates with which they diffuse and effuse. Let's start off recognizing that the two temperatures are equal. And since the two temperatures are equal, the average kinetic energies of the ammonia and the HCl gas are equal. Let's substitute in now what the kinetic energy is. 1/2 the molar mass times the average velocity squared for each gas. And rearrange, getting rid of the halves. We're going to divide through by the average velocity of the HCl squared. We're keeping the ammonia up on top because I want the faster velocity on top. And you notice that we have the molar mass of the HCl on top when we divide through by the ammonia. Notice that when we have this reaction, when we have this equation, the gases are catty-corner across each other on either side of the equal sign. Taking the square root of both sides, we get an equation which we're going to expand on in a moment on the next slide, where the average velocity of the ammonia over the average velocity of the HCl, which is going to be a number greater than 1, that's why I have the ammonia up on top, is equal to the square root of the molar mass of the HCl over the square root of the molar mass of the NH3. And since the HCl is heavier, that's going to make that greater than 1 as well. Finishing it up, let's take a look at how to use this for a calculation. So Graham's law of effusion is given by this long equation where we have the rate of effusion and the velocity of a gas are both essentially the same thing. A rate is just a change in something with change in time. Velocity is a change in distance with a change in time, and it turns out that the rate of effusion and the velocity are related to each other. And there's the molar mass of gas B over the molar mass of gas A. And again, I have the faster, lighter gas on top with the velocity. I have the heavier gas on top in the molar mass. If you flip this upside down, it's no big deal as long as I said, you do have the A caddy corner across the equal sign from the velocity to the molar mass and the B caddy corner as well. I've got this outlined because this equation is on your reference pack. It's part of chart B, and make sure you go and find it so you know what it looks like, because it won't be given to you on the test. So here's an essential calculation. What is the ratio of the velocity of the ammonia molecules to that of the HCl molecules? So let's plug some numbers in. Start off with the rate of the ammonia over the rate of the HCl. That ratio is what we're trying to find. If I were to ask you for a specific rate, I would have to give you the rate of one of the gases. So if I gave you the rate of the HCl, you could actually calculate the rate of the ammonia. In this case, I'm just interested in getting the ratio. Plug this in. We have the square root of 36.5 grams per mole divided by the square root of 17 grams per mole. And that equals 1.47. It does equal the square root of 36.5 over 17.0 as well with your algebra. So 1.47, or almost 1.5 times faster on average, is how fast the ammonia molecules move compared to the HCl molecules. So you'll see a couple of problems like this on your homework. Again, make sure you help each other out to understand how to set the problems up. As I said, if I give you a particular rate, then you're going to have to use that and multiply by that rate. If I give you the ratio of the rates, then make sure you put the correct molar mass up on top. I'm always going to give you a ratio that's greater than 1, so make sure the molar mass of the heavier gas always goes on top in the square root. All right, I hope you've understood what was going on in this video. If not, you can go back and watch it again, or again, talk to your colleagues, talk to your lab partner, and good luck on the homework. See you tomorrow.